Hi, welcome to the last video in this alum adventure. Here is my solution, in which crystals still have not formed yet. It has just been sitting on my desk undisturbed with the Chem wipe on top to keep out impurities, and the solution has been evaporating, but since crystals still have not formed, the solution must not have been saturated completely. Moving on, what if I wanted to grow one giant alum crystal? There are two things to consider. How much energy does it take for little particles to crash out of solution into little crystals, and how much energy does it take for particles to latch on to those and keep building crystal structures? Lowering the temperature will cause the solubility to go down. This changes the equilibrium and causes many little crystals to crash out of solution. After those many initial formations, the goal would be for one giant alum crystal. So after lowering the temperature briefly, I would store the crystals at room temperature so that other particles latch on to the newly formed crystal, causing one giant one to form from the jump-started little crystals. Now let's talk about X-ray diffraction. If you grind up alum and shoot X-rays at it, the X-rays will go between a plane or two of the crystal structure and then bounce out. This graph shows the intensity of photons bouncing out. They are waves, so when they bounce out in phase with each other, we see peaks in the graph. So how do we read this graph? The wavelength of the X-rays is about 0.15 nanometers. The angle of diffraction shows that the steepest peak is around 2 theta equals 22, which means theta equals about 11 degrees. Then we can use Bragg's law to figure out the d spacing between the planes of the crystal structure. In Bragg's law, n represents an integer value that just depends on how steep the angle of diffraction is. The path length value is an integer multiple of the wavelength. Here, we'll just use n equals 1. Solving for d in this equation shows that the d spacing is 0.404 nanometers. Knowing the d spacing gives us a piece in the puzzle to figuring out the crystal structure of alum experimentally, because it shows how far apart the layers of the structure are. That ends our alum adventure for now.